Welcome everyone to Remoticon, and depending on your location, good morning, good afternoon, and good evening. And today we'll be talking with Eric Schlaepfer on PCB reverse engineering. And Eric is a hardware hacker, cathode ray tube aficionado, and enjoys both forward and reverse engineering. He's known for his Monster 6502 microprocessor, and his Snark Barker sound card. So with that, I'd like to introduce Eric. And if you have any questions or comments, put them into the sidebar in the chat. But most importantly, you can unmute and ask him the question directly. So Eric, welcome to the talk.
All right, welcome everybody. Thank you so much for coming. I've been looking forward to this for quite some time, and I really hope you all enjoy it. I've been to one of the other workshop sessions, and one of the things that I wanted to do a little bit differently in this workshop is I really want it to be a hands-on situation. And so I have some slides and stuff prepared that I'll go through to kind of give you an introduction to the subject. But really what we want to do is dig in to the circuit boards that I hope you all brought. And what that means is that you should be prepared to show me the board on camera and unmute yourself and ask me questions if you're getting stuck at one particular point when you're working through the reverse engineering. I am here for you today. And so we'll have a lot of fun doing that. So let's go ahead and actually, yeah, I've got some questions coming in about some of the computers behind me. Those are some of the computers in my vintage collection. So things that I reverse engineer to fix, or things that I design hardware for. It's a really interesting way to sort of practice my electronics hobby. So I guess we can talk about that later if we have time. Anyway, I'd like to start by going through a short presentation. This presentation is divided into two halves. And so we'll do the first half. We'll do a little bit of hands-on type stuff. We'll take a break, do the second half, and then do the second part of the workshop. All right, so let's go ahead and talk about reverse engineering circuit boards. So first of all, I want to make sure that you all brought a circuit board, and ideally you want something that is a 2-layer board and something that's reasonably straightforward, probably less than 100 parts. Otherwise, it just starts to get to be a bit of a pain to do in 2 hours. If you have one that's more complicated than that, that's okay. Just don't plan on finishing it in 2 hours. And if that's the case, that's okay. You can always finish it up later with the techniques that you'll learn today. So a couple of tools that you're going to need. A flashlight will be very useful for you. Soldering tools are optional, but recommended. If you have trouble getting to a trace, you may need to remove a part so that you can see underneath it. And then finally, you'll need some software. For image editing, I prefer the open source GIMP, but if you have Photoshop, you could use that too. I will not tell you how to use Photoshop because I don't know how. And so my demo here will be focused on GIMP. And then for the schematic capture, we're going to be using KiCad. I guess you could use Eagle, whatever you're comfortable with, but the demo's all done in KiCad. Are you all ready? Everybody's ready. Of course they're ready. All right, so I want to talk about the two basic kinds of PCB reverse engineering. The first kind is what I call a block diagram / BOM level or bill of materials level. And when you pay a professional company to reverse engineer a piece of hardware, typically this is what they'll give you. So they'll give you a nice fancy report with a bunch of images and stuff like that, and a parts list, usually fairly detailed, although a lot of the jelly bean parts they'll just leave out. And the idea here is that you can kind of get a general idea of how the product is constructed, how the board works, what are the big basic blocks inside that design. Now, the second kind of PCB reverse engineering is a detailed clone, and that's where you go in and you back out the entire schematic and potentially even the PCB. And so that's what I did with the Snark Barker circuit board. I started with the Sound Blaster sound card and then reverse engineered it to get the schematic and then back engineered the layout as well. So I wanted to show you a quick example of what it looks like to do a block diagram level reverse engineering. So this is a device called a whistle pet tracker. a whole pile of these wound up at the local surplus store, and I bought one because it was really cheap, and I was kind of curious to see what was inside it. And so what I did is I took some pictures of the board and kind of went through and identified as many components as I could. And so you might see something like this in a maybe slightly less than professional report. And so you can see that there are some major items here, like there's this RF microcontroller, there's an accelerometer. I've taken the liberty of pointing out a couple of the other components, like there's the diode and some other parts, but I don't have any connectivity information. In other words, there's no netlist, there's no schematic. All I know is what parts are on the board. And I can still learn quite a bit from how this device works just by understanding what devices are on the circuit board. If you flip the board over, there's a couple of other interesting parts too. So there's actually an SoC and some crystals and some flash memory. And so you kind of get a general feel for what's in there. In fact, there's even a, oh, somebody wants my picture in the top right. There, how's that? Is that better? Okay, so where was I? Oh, yes, and you might also notice that this particular device has the infamous Chinese spy chip as well. Okay, and this is a different device. This is a snappy video snapshot, and what I've done here is put together a block diagram with a schematic underneath it. And so this is the result of a couple of hours of reverse engineering work on that board. And so this, if you don't know what a snappy video snapshot was, back in the 90s, all you had was a parallel port to connect peripherals to your computer, parallel port or a serial port. There was no USB at that point. And so if you wanted to do something like, oh, I don't know, digitize analog video, then you would have to buy this little video snapshot, which would plug into the parallel port, and that would acquire the signal, and then the software would actually turn that into a video image. And so it's a very clever design using an FPGA and some other stuff. If you don't know what I'm talking about with parallel ports, then you're just going to have to look at this meme. Okay, moving on to the start of the reverse engineering effort. First thing that you need to do is put together a list of all the components on the circuit board. And there's a particular way of doing it that I like doing it. You can do it whatever way you want, but the basic information that you'll need is the component designator. So hopefully your circuit board has silkscreen markings on it that show you what the designator is. And you also need the package type. And so you look at the part, and you can use experience, you can use Google. There are some guides that you can find online on various surface mount part package types. And as best as you can, identify what that is and then type that in. Somebody actually had one of those snappy gadgets. That's great. I like that. And of course, it won't work with a modern OS because, yeah, reasons. And you also want to store the marking information. So look at the top of the chip, for example, and anything that's on there, anything at all, just type that up into a cell in that spreadsheet. And so you can see I have an example here started where there's a transistor and a SOT23 package with the K1N marking. And here I have not identified what that part number is. And that's okay. That may be okay for the reverse engineering effort you're doing. It may be enough to understand how the board works. And then some of the others, you could see I've filled in part numbers and various other pieces of information. Okay, so here's another example. This looks like a transistor. The designator is a T1, T for transistor. Typically Q is more common, but I've also seen T. The part here is a SOT23, and I just happen to know that from experience. But like I said before, you can actually Google part package types, and you can get a visual reference guide to see what each of those different packages look like. And that can be very helpful. Then you can also see that there's a top mark on here. It's 13G. And so often what you can do is search Google for quote 13G unquote, and then the name of the package, and you'll start getting parts just coming in that might be possible candidates. Now, obviously, if it's not a transistor, then you can discard it. You kind of want to filter just by parts that are transistors in this case. And then eventually, if you're lucky, you'll even find a part number for it. Okay. Now, you might notice, depending on your board, that there may be components with no markings at all. A common example are most surface mount ceramic capacitors have no marks on them. What you can do for that is desolder it and then measure the capacitance with a multimeter that has a capacitance checker mode. Or you might have a fancier LCR meter that you can use to get a more accurate reading. So anyway, you could take that value, that goes in the spreadsheet. Resistors, a lot of them do have marks on them. Those really small ones do not, and you'll have to take those out of the circuit and measure them with a multimeter. Now, if you don't know what it is, you don't want to have to remove it from the board. You might be able to figure it out. So, a lot of component data sheets for chips that are, that require a lot of external circuitry, they will give you a typical application circuit, and that circuit will often have recommended component values in there. And so, by looking to see which pins those discrete components connect to, you can often figure out what the probable value is of the part. And so when you're done with all of that, then you can put together a block diagram. But for that, let's go ahead and launch into the practical part of the presentation. So I'm going to go ahead and switch my views. And we're going to look at the board that I am going to reverse engineer today. So yes, I'm going to be reverse engineering a circuit board with you too. Hold on, let me go and manage some slides here real quick. Give me one sec. Okay, so I hope you all have your boards with you. Let me go and switch my cameras around a little bit so you can see me still. So this is my circuit board. I actually did bring some high resolution photos, but they're in my backup slide section, so I am managing that right now. Here we go. Let me go back to this view. All right, this is much better. I apologize for the other camera. It's the only other camera I own, and it's NTSC. So I'm calling it the Potato Cam 2000. All right, so this is the circuit board that I brought. This I found in my junk box. I'm not really sure what it is. You can see it's a mix of through-hole components and surface mount components. And so there's one chip here. It looks like something that could be a voltage regulator up here. And it's also got some wires coming in. I may have to move those out of the way so I can see what some of the other components underneath it might be. It seems like it's pretty well labeled on here. So we're going to move into the hands-on part of the workshop where you bring out your circuit board and start putting together the bill of materials. So I'm going to go and see if I can share that with you. Let's go and get that out of the way. I'm going to go ahead and fire up LibreOffice because we got to be all open source software here. And so let's do Designator. And by the way, you can sort of stop watching me at this point and start watching your board, because what I'm going to do is go through this entire board and I'm going to type up every component that's on here. And so at your end of things, I want you to bring up a spreadsheet, start doing that with yours too. Now, if you have any questions, you can ping me in the chat. And so hopefully I'll look over periodically. I'll be able to see that and then answer any questions that you might have. If there's a component on any of the circuit board that you're trying to reverse engineer and you just don't know what it is, then please share it with the rest of us. So go ahead and unmute your microphone, turn on your video, and show us the board, and I'll do my best to try and identify it. And if I can't, then perhaps somebody else in the room can actually do that. Somebody's got a NICSI driver board. It has chips with Cyrillic writing and date codes of 83. That would be a wonderful board to look at. Sebastian, if you don't mind, go ahead and show us that on your video. Let me see if there's something I have to do here. You should be able to do that. Yeah, if you don't feel comfortable sharing or turning your camera on or anything like that, that's absolutely fine. Don't worry about it. Yeah, so some of those Russian chips can be very interesting. The hardest part is figuring out the characters to type into Google, but it often does work. Someone else has a board that they have the bill of material for and soldered together myself. Hope I'm not cheating too much. I think that'll be okay. High voltage binary decoder. Yeah, there's a NICSI tube driver that's pretty well known that we'll be using. Okay, so designator, I'm not putting in quantity, I'm putting in package type. I'm going to put in top mark and part number. Okay, so let's have a look at my board now. C1, there's a good start. I should probably start with a chip though first. All right, let's do U1. The package is DIP. I think this is a 14 pin. 7, yeah, that's a 14 pin DIP. And the top mark is MC 1374P. And then on the second line, it says KHAL 9311. That's probably the date code. So I imagine that's the 11th week of 1993. So either that or the 93rd week of 1911, but you guess as to which one is more likely. And then the part number is, well, obviously that's going to be the MC 1374. And this is also where Google comes in handy. And so what I can do is actually figure out what that part number is. MC, what did I say it was? 1374. No one's commented on my search history, so that's good. This is a TV modulator circuit. Oh, that's interesting. That's a really interesting looking part. Yeah, somebody else already looked it up, looks like. Yeah, blind vias, I wouldn't recommend doing a board with blind vias. It's starting to get a little too complicated. Someone on YouTube asks, why do you need to take the components out of the circuit to measure them, i.e. resistors? Couldn't this be determined in the circuit with the voltmeter? Well, the answer is you can try. Problem is that there are often other components in the circuit that will throw off your reading. So for example, let's say you have 2 resistors and they're wired in parallel on the circuit board. If I come in with my multimeter and I try to measure the resistance of one of those resistors, the value that I'm reading is actually the resistance of those 2 resistors in parallel. And so other elements in the circuit will influence the reading. The same thing goes for capacitors. Trying to do it in circuit, you're just not going to get an accurate reading. Yeah, so unfortunately, the screen is a little blurry. Trying to think if I can, well, I have an idea. Let me try something. Bear with me. 1 minute. Okay, so I'm going to do a Zoom screen share instead, and we'll give that a shot and see if that works any better. So please let me know what that looks like.
That looks
great.
good?
Much better. Okay, so TV modulator circuit. The MC1374 includes an FM audio modulator, sound carrier, RF oscillator, and RF dual input modulator. Okay, that's informative. Oh, it generates a TV signal from audio and video inputs. Okay, this board is actually a lot more useful than I thought it would be. I had it in my junk box, but as it turns out, I might be able to use it to act as an RF modulator for some of my vintage game consoles and computers. So I can hook it up to a vintage RF input television. So now I have a good reason to go and reverse engineer it. And look at this, simplified application. And so here they have a circuit diagram with some component values in here. And so if I can't figure out any of the parts or the part values, I can refer to this diagram in the data sheet to kind of figure out what they recommend I put in. So I'm going to go ahead and go back and just start entering more of these parts as I find them. So here's U2. This one is, looks like somebody's pinging me. Hold on 1 sec. I have a SOT23 package with markings EH, ideas. Okay, I would recommend you Google for quote EH and then SOT23. And then if you have the designator, if the designator begins with a Q, then it's probably a transistor. If it begins with U, then it's probably, okay, somebody was just pinging me what the video quality looks like. Okay, good, that's solved. And if it's a U, that means it's a chip. Okay, I'm gonna go ahead and go back here. This is a TO220. I hope that answers your question. By the way, if you want to ask me a question over audio, please feel free. I want this to be an interactive. Okay, so this is 7808. I'm sure you can guess what this is. CT. Oh, there's an MC at the beginning. Oops, did not want to do that.
I did have one question. How do you tell the difference numbers on a package? How do you narrow down, okay, this is a date code, this is probably a part number? Because some chips I see that I don't know what's what.
Yeah, that can be hard sometimes. Google is kind of your best bet. So if there are multiple lines of text, then put in both lines separately with quote marks around them. And so if one of them doesn't really turn up any results, Google will often automatically drop that. You can also experiment, and so you could search for one line versus the other line. You can also truncate the part number. So if it's got letters at the end, you can get rid of those and just search for the first couple of letters and numbers. Date codes in general are in the form factor where they'll have a 2-digit year and a 2-digit week number. And that's basically the number of the week in the year. So January 1st would be week number 1, and so on and so forth. And so if that number is greater than 52, then it's probably not the week number. And conversely, if the year digit number, the 2-digit number, doesn't make sense, so if it says like 33, possibly referring to 1933, they didn't make chips then. And so obviously that's not really going to be what it is. Now, other manufacturers will use different coding schemes. And so this is just the most common one that I'm telling you about. So on this one right here, KHL9311, the first 4 letters, they're probably for the fab that they were using. So it could be like a fab and assembly lot number. And then the last couple of digits are the date code. But not everyone does it that way. Okay, so this one right here, for example, this 7808, it just says QHL317. And so that's going to be in their form factor. I don't know exactly what that code means. So that seems like some specific Motorola thing. So I'm just going to leave that off for now because I already know that what this part is a LM7808, which is the 8-volt version of 7805. Yeah, that's also handy. So somebody pasted a link to an SMD codebook, and that's going to be very, very useful to refer to. And somebody else already said that it's an 8-volt regulator. I don't even need to do any work. You guys can do it all, except you have your own boards, and I hope you're doing the same thing on your board. Okay, so let's get some of these other parts in here. So those are the 2 chips. I wanted to do those major components first, and so I'm just going to go and blast through here. If your board doesn't have a designator, then what I recommend you do is go on to the next step of the process where you take a nice high-resolution photo of the top and the bottom of the board. And you don't have to use a really fancy camera for that. You could just use your cell phone if it's got a decent camera on it. If you have a scanner, then you can put it in the scanner and use that to get a high-resolution image. Now, that's important for when your board doesn't have a designator, because then you can pull that image into GIMP and you can superimpose your own designator on top of it and then put that into your spreadsheet so you'll know what you're referring to. Now, if you do it that way, I recommend that you add that as a separate layer. And so that layer will hold all of those text elements. Okay, let's go ahead and get these added here. C1, R1, R9, and R5. So C1, obviously, I don't know what it is because I haven't measured it and there's no marking on top. R1 is 273, and so I'm going to enter that in here, 273. That's actually 27 kilo ohms. Because what they do is it's kind of like resistor color code on a standard colorful resistor. It's just that instead of colors, they just put the number on there. And so the first 2 digits are the value, and then the last one is the number of zeros at the end. Okay, so R9 is 393. I also look at it upside down because sometimes they make sense both ways. But this one is 39K, so that's good. R9, let's do 39K. Sometimes designators are one-to-one from the example diagram in the datasheet app note. Yes, that's an excellent point. That's another good trick. See, I knew this would be good as an interactive workshop because people here have so many awesome tips to offer. This is great. This is really good. I'm definitely going to be learning things here today too. 184, yes, go ahead.
Oh, sorry. Would you be able to reflash the board that you're reverse engineering? There's some people who just jumped in and are curious about what exactly you're looking at again.
Yeah. So I can actually move my slide presentation back over here again. Shoot, there we go. Okay, so this is the board. It's called On Command Video, and I'm starting to remember where I got this from. I pulled this off of the back of a really weird 2/3 form factor VHS VCR that was designed to run off of 12 volts DC. And I think it came out as some sort of a video on demand service where you would like dial in some number or something, and then it would automatically play the tape that was loaded into the player. And so this is the video interface board that I pulled off of the back. Great suggestion. Okay, where was I? That's
sorry,
R5.
Eric.
Yes, go ahead.
I have a suggestion for part that I actually can't find, but
Okay.
as I said, I do have the BOM, so I can find it if you want. But it says 7BD84Y. That's an 8-pin package, very small one.
Okay, so do you have a picture of the package, or do you have video of the package? Because there's a number of different types
I can try to give you that's the tiny little black square there.
Okay. All right, hang on. I need to try and find the video.
Can you see the
Hold on
square?
one sec. Hold on one sec. I'm trying to find your video. I'm a little new to the whole Zoom thing, so I'm having trouble.
Yeah, that's the one labeled ABBE. ABBE.
Give me one sec. Sorry.
Yep. It was quite a small package.
Shoot, how do I bring somebody's video into focus? Oh, wait, there we go. This one, here we go. Okay.
Yeah, so slide the switch over on the side, and you have a tiny
that's
square.
tiny. So
yeah.
So it's got 8 pins.
Mm-hmm.
Huh, that is a little bit odd. That I would say is a DFN. Does it have leads on all 4 sides or just 2 sides?
2 sides.
2 sides, yeah, that's probably a DFN. One of the other tricks that you can do is if you have a ruler calibrated in millimeters or a set of calipers, pardon me, that's my clock striking the hour, if you can hear that. But what you can do is actually measure the dimensions, the X and Y dimensions of the chip. And if it might be something like 3 by 3 millimeters, in which case now you know it's a 3 by 3 DFN package.
Yeah, it's 3 by 2.9.
Okay, excellent. So call it a 3 by 3. And so what you would do then is search for 3x3 DFN and then put in what that top mark was. And that should help you track it down.
DFN, you said?
Yeah, 3x3 DFN.
Right.
And then just plug in the top mark, and you should start seeing results. Now, they may not be exactly what that part is. One of the hints that you might get is to look at the circuitry around it. For example, if it's near a USB connector, it might be some kind of USB surge protection device.
I'm pretty sure it's actually a voltage regulator.
Oh, yeah, voltage regulator. That's a good one. Yeah. So you can also add those keywords. So if you have guesses as to what it might be, you can add those to the search terms and try and narrow things down. It's a little bit of an art, and it takes some practice, but I think you'll find that that it gets easier with time. Okay, so I'm gonna go ahead and figure out some of these other resistors here. So this looks like this is 180K. I can type correctly. R12 is 2K. Yeah, these are all very large resistors, and so I'm not expecting anything out of the E12 series, which would be like a 5% resistor. Okay, so here's an inductor, L3, and it says 120 on it. So I'm going to put that under top mark. Inductors are tricky because the manufacturers label them in different ways. So for example, 120 could mean 120 nanohenries. It could mean 12 nanohenries. In other words, 1, 2 with no zeros after it. It could mean 12 microhenries. I don't know. And so I'm just going to leave that alone for now until I have a better idea of what it should be. Now I could also go and refer back to the data sheet. And the data sheet might give me an idea of the range of values that would be acceptable for that component. I'm going to take a look and see if there are any other comments here. Yeah, smanuals.com/SMD, that one's a really good one. Mystery transformers will have some windings with 0-ish ohm resistance, so you can identify which winding is which. Yeah, identifying transformers can be very, very tricky, and that's kind of a whole separate ball of wax. I could do an hour-long talk just on transformers. So I'm going to go ahead and go back here. Let's finish this up. C7, Q3. Actually, let me do C3. That has a marking on it that says 334, and that is 0.33 microfarads. And I'm just looking at the physical package. It looks like a dipped ceramic capacitor. So experience does help a lot. And if you don't have the experience, then you can Google around and try and figure it out, or desolder it and measure it. 47 mics, 16 volts. Yeah, so there's some good diagrams that you can look at that have logos of semiconductor manufacturers. And that can also be useful if your chip has a logo on it that you don't recognize, and you want to be able to look it up on the manufacturer's website. The flashlight is good because the lighting at the front of my desk isn't the best. 325, that doesn't sound like the capacitor value. I'm going to look at the other side. Okay, 334, so that's 0.33. So that's another 0.33 microfarad. Okay, other labels include 63WG4 and C5H4. Yeah, it's hard to say. It could be a lot of different things. 48-pin QFP, TI labeled C2025. That may be difficult. It might be a custom TI part. That's a tricky one. Anybody here used to work for TI? Maybe you can look it up.
I have a question.
Yeah, go ahead.
Yeah, so I have a board with 2 unlabeled ICs. I can shoot.
All right, let me go and see if I can find. What's your name so I can find you in the list?
Inne, I-N-N-E.
I-N-N-E. This is not in alphabetical order.
Ooh.
Thank you, Zoom. Thank you.
Do you have feedback on my microphone or?
Yeah, let me go and see if I can see it on the list.
Just going to mention if he's
there you are.
speaking, he's usually going to be near the top.
Yeah, there you go. Look at that. Okay, so you have an 8-pin SOIC. That's the U2 in the middle.
Yeah, the
and
2 ICs?
Yeah, and Q1 right there next to it, that is a transistor. Q stands for transistor on the designator. And it looks like it's SOT23. It's a little hard to tell from here with that camera. And then on the left-hand view, that is also an 8-pin SOT23, and I can't read the designator. That might also be, oh, is it L?
Which one? Sorry?
So I'm looking at the left hand of the image that you're showing, and that device directly above the crystal looks like an 8-pin SOIC.
Yeah.
Can't read the designator that's next to it on the left.
U1.
U1, okay, all right.
Yeah.
So you have 2 chips then, and they're both in the same package.
Yeah, so it's a...
I have a tip. One of those, U2, that actually might be a transistor. So just keep that in mind as you're searching around. They may have actually labeled the transistor as a U instead of a Q. So it does happen sometimes.
Yeah, so it's a remote-controlled haptic feedback device.
Okay.
So I think one of them should be a RF receiver, and the other one should be a motor driver.
That's a good guess.
So the right one is connected directly to like the battery and the motor.
Uh-huh.
So, but like they're not marked with anything. So should I just go for the cheapest one?
Put down blank. You just put down blank, and we'll figure it out later. One of the things that will happen in well, I haven't decided exactly when we'll do this, but at some point we'll switch modes, and we'll start talking about imaging the board, and then starting to trace over it. Now, the board that you have, you might actually have to desolder those. And
Okay.
you could do it with a soldering iron, but if you have a heat gun, that would be even easier. And so you can just pop that right off. If you can't do either of those, that's okay. We can just try and guess at the connections. And I'll kind of show you a couple of techniques for doing that. Somebody else has an 810 SoC with no top mark in a really simple RGB LED lamp. Is it likely an AT Tiny? You know, it's hard to say. It could be anything. A lot of stuff that comes out of China, particularly the high volume electronics, they won't put labels on any of the chips because they're trying to prevent competitors from reverse engineering it. So my guess is that it's an LED driver chip that's special purpose. And so it may not be a microcontroller. But again, it's hard to say unless you have the whole board and you're looking at the whole board to figure out what other components are on there. So for example, if the board already has something that you know is an LED driver, then it very well may be a microcontroller. It may be something else. I hope that answers your question. Yeah, Clive.com has some excellent teardown videos. And so you could also watch those to gain some more experience identifying some of these chips. All right, so let me go ahead and enter a couple more of these. I may not get to all of them because I do want to move on at some point and start talking about how to actually image the device and then start tracing it. So I have a question here, which is kind of interesting.
One more quick question?
Okay, go ahead.
So I have on my board a couple of connections that aren't bridged. They have like solder bubbles on them.
Those are great. Yeah. So you've got two component pads, but it's got a solder bubble on it that basically it's like a jumper. And so that's a manufacturer's option. A manufacturer's decided that they want to jumper the board a particular way. And so either they'll put in a 0 ohm resistor or they'll put in a solder jumper. And you can actually model that in your schematic. And so you can drop down a jumper that's already got a wire across it and then figure out what it does later. And so hopefully it's easy to trace those connections.
But they're not jumped, so they're not connected to each other.
Okay. So there's a secret function in there. Might be fun to jump it and see what it does at some point.
Okay.
R1AN. All right, so I'm going back. I have a transistor, and I think that's an R1AN, but that might not be the number one. It could be an uppercase I or a lowercase L. And so if I go and Google that, then I'm going to have to figure out a couple of different options here. And this also looks like a SOT23. It's slightly larger than that, and so it might be some manufacturer variants. But that's okay. I'll leave that alone for now. So here's C13. C13 is a trimmer cap, and I don't know anything about it. I'll probably have to desolder it to figure out any of the characteristics. It has a part number on it, but there's a good chance I won't be able to get any hits on Google. Okay, so let's see what else.
What do you do with epoxy blobs?
Well, I just leave it as an epoxy blob, and if you have access to something like fuming nitric acid, you could probably remove it and see what's underneath it, but that is outside the scope of this workshop. So I know a few people that work with fuming nitric acid, and it is really nasty stuff.
Fair enough.
Okay, R17, this one's a 100 ohm resistor. And let's see what else we have. I have a C that I'm gonna have to put a question mark next to because the rest of that designator went underneath a via. So there's a via right there and it clipped the number on the designator. Oops, I hate it when that happens. So I don't know what that is, but we'll figure that out later. And there's a Q5. Let's see if the Q5 has the same top mark. So I'm gonna look at this on camera again. 2A. 2A. That happens to be 2N, no, sorry, that would be MPS 2222A, I think. I'm pretty sure. Someone else in the chat could probably look that up for me, but 2A is a very common top mark, and it's one of those really basic jelly bean transistors. And then we have two unmarked resistors. These are through hole. Oh, you know what? They stuck the number underneath the resistor. Well, that's a pain. Okay, so this looks like so I'm actually shoving it out of the way. I'm pushing the resistor with my fingers, and I'm looking at it with a flashlight helping me. So that's R19, and the value of that is 680 ohms.
One tip for looking at chips is that most cell phones have pretty dang good cameras on them that you can use as a microscope.
Yes, That is an excellent tip.
These as well. These are the loops.
I was gonna
Pretty
say
good.
you can also
Yeah, those little eye loop thingies can be helpful, but the quality of the optics usually isn't all that great. If you have an inspection microscope, of course, then use that by all means.
My little life hack was I bought a old document camera from school surplus for $5, and it has something like 30x zoom on it.
Oh, that's fantastic. That's great for reverse engineering. L1 is 270. L2 is 220. I'm just kind of working my way across the board. It's probably okay if I leave a part out. I'll catch it later. CR1, that's a diode. And let's see if the diode has a marking on it. It's one of those glass ones. R1N, I can't really read it. I would have to desolder it. So I'll just leave it alone for now. So I'll just call it 1N question mark. And we'll leave that alone. Here's another one, CR2. CR2 is a 1N 4000, probably 4001. This thing doesn't really have anything high voltage on there, and the 4001's got a 50 volt reverse voltage on it, so that should be okay. R15 is a trimmer, so that is a trimmer potentiometer, and let's see what it looks like. That is a 1K. I don't know what taper it is, probably linear, but who knows. All right, let me rip through a couple more components here. I got some more transistors. That's cool. Let's see if any of them are the same. Another 2A. Q2 is R1AN. And Q1 is another R1AN. If I'm lucky, these are just NPN and PNP complementary pairs. R13 and, okay, just a few more parts. R4 and R2. So I should probably save this. Huh. Looks like I already had one. Okay, R13 is 560 ohms. And 1.8K. And R4, 4.7K. And R2 is another 560. 7. Almost done. I'm going to do the connectors and then we'll get back to the presentation. 750. Okay, C4. And C4 is probably another one of the same. Yes, 47 microfarads, 16 volt. Okay. Let's throw in some connectors. They actually have labels on the silk screen, so I know what they do. And J3 is video. 2A is a 2N3906 PNP generic transistor. Awesome. Yeah, I knew it was something common. I thought it was 2222, but 3906. My brain is not quite as good as a Google search. It's funny, there's a friend of mine who memorized every single one of the 74 series TTL part numbers. So I could tell him 74LS74, and he'd say, oh, that's a dual flip-flop. What a guy. And C2, I think I missed C2. I guess that C2 is probably a 0.1, but I won't be able to tell because it's probably wired in parallel with a number of other 0.1 microfarad capacitors. But that's okay. All right, and this last connector does not even have a designator. It's just called DC in, but I'll give it an entry anyway. Is that it? I think that's just about it. And again, if I missed any parts, I'll go over it again later when we're doing the schematic capture part of it. I'm gonna guess this is probably meant to be J1, but I'll call it IR switch. So that's what it's labeled. Okay, so now I have more or less a complete bill of materials. And there's some parts that I probably need to look up at some point. I already did the main one though, which was that Motorola part. Let me go and see if I can share you the data sheet again. Okay, so here's our data sheet. And we can look at some of the components that are in here. So L3 and L4, these are 0.22 microhenries. In other words, 220 nanohenries. And this corresponds with the top marks that I read off those inductors. And so what that tells me is that the values here, these top marks, where were they? Yeah, 120, that's probably 120 nanohenries. And these guys right here, goes in the wrong columns. This is probably 270 nanohenries and 220 nanohenries. And I think those were all the inductors. I think there were just 3. Let me take a look again. 1, 2, and 3. Yeah, so only 3 inductors. IR switch might be 2 headers, 1 IR, 1 switch. Most likely it is. So most likely it's just 1 header strip comprising 2 distinct headers. Yeah, so I'm not skipping the headers. They're just down here marked IR and switch. In fact, I'll separate those out. So IR and switch. Great. Okay, let's go back on to the data sheet. And we even have a couple of capacitor values here and some resistor values. All right, this is actually going to be very helpful later on when we start coming up with our schematic. But I think I'm in pretty good shape to move forward. So I'm going to go ahead and save this. And before we switch gears, what I'd like you guys to do is let me know if you're good to go for a little bit longer or if you want to take a break. You know, get up, stretch your legs, maybe get something to drink. You know what, why don't we do that? Let's just take like a 5-minute break. Listen to Biden, all right.
I think I'm still on screen with my camera. I don't know if people want to see me writing stuff in my notebook, but
yeah, I'm no longer sharing your screen. I've just got my screen going right now.
By the way, Eric, I think I actually found on the bomb what the tiny little circuit was.
Oh, you really? Okay.
It's a PCA 9306 dual bidirectional I2C bus and SM bus voltage level translator.
Yes, yes, I've actually used those before. They're great.
But I still can't find it from the markings on the top of the chip.
Oh, interesting.
Good thing I still have the bomb.
Yeah, does the data sheet have a top mark section in it?
Usually it's
Because
the bottom
sometimes
of the
you can go through there.
data sheet.
Usually it's at the end.
And let me check.
The first workshop today to recognize the election results. Yeah, exactly. Now, I try to stay away from politics on my public tube time persona as a matter of practice, but let's just say that I was smiling a lot today.
So it's going to be above the like package outline stuff, or?
Yeah, so look towards the end of the data sheet. Actually, I'm going to pull
Mm.
that up too because I'm kind of curious myself. Let's do. $93.06, was that it?
I think so.
Okay.
Yep, 93.
Oh, here we go. Top side mark. So I am on page 3.
All right.
And so they have a couple of different numbers here, like 306P or 306C. P6X is another one. I forget which one yours had.
Give me a sec. That's 7BD84Y.
7BD84Y. That is
That's
really
what I can
odd.
read. Yeah.
You know, it could be that it's not an NXP part. It could be that what you have there is a compatible part from TI. So I'm pretty sure TI has a part that's footprint compatible with the same function. And so that might be what it is. It may have gotten substituted at some point.
Actually, the datasheet that I have up right now is a TI one.
Oh, it is. Okay.
Yeah.
Interesting.
Let me see if I can get...
All right. Well, we'll keep that in mind because when you're going through and you're putting together the schematic, if any of it doesn't make any sense. So for example, if you're looking at the circuit and the IC isn't really connected in a way that makes sense, for example, power and ground are on the wrong pins, then those are indicators that you've identified the part incorrectly and that it's time to go back to Google and try and figure it out. Yeah,
I'm reading off the BOM that I actually got from the guys who designed it. So.
Oh, you did? Okay.
Yeah. but actually, in the TI datasheet, I can't find anything about the top marking.
Yeah, let me go and take a look at the onsemi datasheet. Yeah, they have a couple of different top marks here as well, but none of them sound familiar.
No.
Yeah, well, it's not always 100% thing. I mean, you know, if they had this fabricated in China, then whatever contract manufacturer they used might have substituted and might have purchased it from a local vendor instead of from onsemi or TI or even NXP.
Sure.
Eric,
yes.
I had a question around this, basically the same subject. If you were to get a board that was kind of just a cheap Chinese board, but they had intentionally removed the markings from the ICs, do you have a kind of method you go about figuring out what chips those are under the covers?
Sure. So there's a couple of things you can do. At this stage in the reverse engineering effort, I would just put it down as unmarked. And then when we go to the next stage, when we start drawing up the schematic, instead of putting down a symbol for a part that you don't have, put down a connector symbol that has the same number of pins. And then try and get it as far as you can in the schematic reverse engineering. So have as much of the rest of the circuit connected as possible. And you might start getting certain clues based on things that are connected to various pins. So for example, if I notice that there's an oscillator connected to it, or I should say a crystal, I can look at the crystal pins and I can look at the total pin count and I can look at the VCC and ground pins. And then I can say, you know, this is a microcontroller. And based on where the power pins are and the oscillator pins are, this might be a PIC microcontroller, for example, or it might be an Atmel AVR, or it might be something else. And so just using those other clues based on the wires that are connecting to that chip, you can make some guesses as to what it might be. Yeah, connectors can be really hard to identify for sure. So that's being discussed right now in the chat room, but a lot of it is experience. If you play with a lot of different connectors, and you've used connectors from a lot of different manufacturers, you could start getting an idea of what a connector might be, even if you don't know exactly what it is. Or you might just look at it and say, oh, I know what that is. That's a JST connector. Or, oh, that's a Molex Microfit 3. Yeah, everyone knows that. So some of it is experience. And a lot of it is just kind of poking around. One thing that can help is if you go to the DigiKey visual search, you can kind of drill down. So you can say connectors, and they'll actually show you pictures of different connectors, and then you can try and drill down from there. Yeah, even Google reverse image search might be useful if you can get a really good picture of it up close, but there's a good chance that their algorithms aren't quite good enough yet.
One also useful thing is, hey, just search for thing, schematic, thing, teardown, thing, whatever.
Yeah, that's
Sometimes
good.
people
You
have
can
already
also
done
search
it, and
for
then
someone else who's done it.
the second one that was like surprising and mind-blowing to me is the FCC website. I'll post a link in a minute, but they will tear down electronics and upload interior pictures, sometimes schematics that the manufacturer has to give them. I
Right.
found like whole toys that, you know, even they'd said like, oh yeah, please do not include this in the public record, and there's still a schematic right there. So
yeah, so the FCC, when you file for the for FCC registration, if your device has radios in it, as a manufacturing company, you're supposed to submit documentation to the FCC, and the FCC will make that public. And so that could include pictures of the inside of your gizmo and all of that. But if I'm somebody else and I want to figure out how your gizmo works, and you've got an FCC number on your product, as you are legally required to do, then in that case, I can just plug it into the FCC database and gather all kinds of interesting information about it. That's another good comment.
So Eric, I just wanted to jump back to my boring chip again.
Okay,
I
great.
just wanted to give you, you were basically right. It's actually in the TI datasheet. I
Excellent.
found that it's called device marking, 7BD,
Okay.
which is the top row of the marking. So it says a package type SM8.
Wonderful. Yeah, so SM8, in fact, if you look up their, sorry, if you look up their package diagrams near the end of the data sheet and you plug in SM8, you can actually find the industry standard name for it. TI likes to use multiple layers of indirection for package names, which is kind of irritating. But SM8 will correspond with, I think it's probably an 8-pin SOT, which is a little bit uncommon, but some devices use it. I'm glad to hear that you figured it out. Sebastian also had some great comments that he left in the group chat, and I want to repeat those for everybody else on the streams. So if a chip is unmarked, check to see if it's really unmarked. Sometimes you can see it with a torch or flashlight for us here in the United States. If you shine the light at the right angle, you can also put some isopropyl alcohol on there and clean the surface and take a closer look. Yeah, removed one is visible underneath the light in the right angle. Yeah, so having a microscope helps. You can clean it with isopropyl alcohol or rubbing alcohol, and then shine a flashlight, adjust the angle a lot, and then eventually you'll get contrast. That works really well for parts that have been laser marked, where the marking is really faint. This was an extremely difficult bit of Googling. Somebody pastes in a link from Amphenol. I'm going to bring that up because I'm curious, and maybe some of the rest of you are too. Amphenol ICC. Oh, this is a battery connector. Yeah. So receptacle and blade, 4-position. Rotoconnect. Oh, I might be wrong actually. So Rotoconnect is that's not for batteries. That's for a pivoting connector. That's really interesting. So it looks like they're marketing it towards lighting products. So probably LED lighting. That's a really good find. Okay, so it's 5:30 now for me in my time zone. We've got about an hour left, and I want to use that time to go through the next stage of reverse engineering. Hopefully, you've all had an opportunity to put together a relatively complete bill of materials for the board that you're trying to reverse engineer. And if not, that's okay. You can come back to it later, but we're going to go ahead and move on to discussing the next stage of the reverse engineering. So let me go back to where we were. Now it is your turn. Okay. Hopefully you all can see this and it's not stuck on my camera view. Let me go back and check real quick. Good. All right, so you should be able to see the slides now. All right, so now we're getting on to the hard part. So top marks have their own challenges. This part is actually getting kind of challenging. Is there a link to these slides? If you need a link to the slides, then you're probably not seeing these. Let me see if there's a way to manage that. Hold on one sec. I guess if I can't do that.
we're seeing them. I think they probably just.
Oh, you are? Okay, great. All right. Yeah, eventually I'll post a link to these at some point later when I get a chance to put them up. Unfortunately, they're not really going to mean too much outside the context of this workshop. So really the workshop here is for you to gain practical experience working with these things. And of course, you can make use of your bookmark function in your browser to bookmark any of these Google resources that came up. I do have a couple of links in here for things like top mark lookups, but honestly, the links that people have been pasting into the group chat are probably better. Okay, great. So let me go ahead and get back to this. I'll also talk with the Hackaday folks about maybe putting the slides up on their website as well. Okay, so let's get on to the hard part. We need some high resolution photos of the top and the bottom of the circuit board. Now, I've already done that for my board earlier today when I had a chance to do that. You can use a cell phone. The trick is you want really good lighting. So do it somewhere where you've got really nice, bright, even lighting, and take a picture straight on with a cell phone. Or you could do it in a scanner. You could use a digital SLR if you want. The key is that you want it to be in focus, and you want to be able to see fine details. So if you need to put on a macro lens or whatever, just whatever it takes to get a good photograph of the top and bottom of the circuit board. And you want to be able to see detail. That's the important thing.
A
Okay.
really good cheap source of light is the sun.
Yes, the sun is great, but it's not always there. For me, it doesn't seem to be there right now. Maybe it is there for some of the others of you. It seems to be kind of random. Anyway, let's talk about the pictures and what you do with them. And so the next step is, once you've got these pictures, is you'll want to pull them both into your favorite image editing suite. So I'm just going to use the GIMP because it's free, and maybe some of the rest of you are using it too. I really hope they change the name at some point, because every time I say that, I cringe inwardly, and I hope I'm not the only one. So what
is called the GIMP?
Yeah, the GNU Image Manipulation Program. So it's an acronym that was rather badly chosen. I think someone thought they were being cute, and this was in the 90s. So anyway, so the idea is that you import the images, and you want to flip the image that represents the bottom layer. And so you've imported them as two different layers. And then once you flipped it, then you want to crop it and line it up using the cage tool. I'll actually demonstrate this for you in a minute, so don't get too bent out of shape. The next step after that is you open up KiCad, and you start putting down all the components from your bill of materials. And so if it's a capacitor, then drop down a capacitor and then set the designator to match. And then just do that for every part that you've got in the bill of materials. Now, if you don't know the pinout, then just use a connector. Just use any old random thing that doesn't specify the function of the device, but just has pins on it with pin numbers. And so that way you can kind of keep track of what you've done as far as reverse engineering is concerned. Then the next step is to trace over the circuit. And so what I've done here is I've marked traces in red that I've already digitized into my own schematic. And so I use that to keep track of where I am, so I don't accidentally try to enter the same wire twice. And if you run into problems, so for example, you might have a trace that goes to a hard to reach place, you can shine a flashlight through the board and actually see where some of those traces go. If you've got the board with you physically, which I hope most of you or all of you have, then you can also use a multimeter, and you can buzz out the connections in diode check mode or in continuity test mode. So something that hopefully makes a beeping sound. Let me try and catch up with the chat room a little bit. There's a fork of GIMP called Glimpse. All right, I'll have to try that at some point. Different colors for top versus bottom. Yeah, so there are some tricks that you can do about that. I'll just overlap them, and I'll show you how that works in a minute. Finally, you can also remove parts to look underneath them. And so here's an example of that. When I was doing the Snark Barker, which is my reverse engineered version of the Sound Blaster card from 1992, what I did, I only had pictures of it. I don't actually have a physical card because they're expensive. But I found somebody on Twitter who did have the card, and that person was willing to remove parts for me and take pictures. And so that individual sent me all these images, and I used those to figure out where these traces went. And so you can see here, there's quite a few traces that go underneath these DIP ICs, and there's just really no way for me to tell where those would have gone without removing those parts. Now, I did not have the luxury in the case of this card. This is the microchannel version of the AdLib sound card, of which there are very few known examples in the world. I think there's maybe only 2 or 3 cards known to exist. And the gentleman in Germany who had pictures of the card was not willing to do any soldering on it for obvious reasons, since it is kind of a collectible artifact. And so he sent me pictures of the top and bottom, and I just had to guess as to where those wires were going. And so I would draw in white what my guess was, and then later on I could go back and fix it if it didn't make sense on the schematic. And so I had to turn on sort of the engineering half of my brain and look at it as an engineer would, saying, well, how would I design this circuit if I were designing it? And I know that some of you don't always have the luxury of experience to lean on, but at least this is a potential trick that you could use in the future. Or you could make guesses and they might be wrong, and you just kind of muddle through, maybe take some measurements, maybe you measure voltages or measure something with an oscilloscope. You can make some more guesses based on that. Yeah, so the red part here is a ground plane that's on the other side of the board. Okay, let's go ahead and dig into the practical part. So these are the images that I made. And so I'm going to go ahead and end my presentation here. And I'm going to go and bring up the GNU image manipulation program with all of its toolbars. And let me go and find where I put those images. Being the brilliant person I am, I did not leave a window open with the files in it. So I have to go find those, while hopefully you can spend some time taking the pictures and getting all of that set up. So let me go and dig for those. Oh, wait a minute, here we go. That looks right. Okay, import. Sure, do whatever you want. Okay, so here's the first image, and I'm going to do an open as layers. Again, I want this to come in as a second layer inside the image. You know what? Actually, before I do that, I'm going to go and I'm going to open that as a separate image, actually. And I'll show you why in a minute. Okay. Oh, it did add it as a second layer. Shoot. Let me just create a blank image and do it that way. The reason is that I need to do some cropping first. Uh-oh. Did I crash it? No, there's a dialog that stole the focus. Okay, there we go. Much better. Okay, so here we are. I've got images of the front of the back. Let me know if you guys need more time to take your pictures. C question mark might be C9, and IR and switch are indeed two headers. Yeah, there's a line in between. Yeah, so it might be C9, but again, I'll work through those once I'm drawing up the schematic. If there's a gap in the designators, then a process of logical elimination would lead me to say that, yes, this is C9, but I won't know that for sure until I get there. And so the first step is to go in and crop. I'm going to use the top one here as sort of the master image, and so I'm not going to crop it all that tightly. So we'll crop that one. This bottom image, I'm going to crop more tightly just to help me out for alignment purposes. Okay. And so we'll copy that, and then I will paste this in as a new layer. And on this layer, let me make sure it's selected. Let's see if I can do a flip. So transform, flip horizontally. And now I'm going to grab the move tool here. And would it have been better to desolder the wires before taking the image? Probably yes, but this is a good example of why it's also handy to have the physical board in front of you. And so you can move the wire out of the way and see where the trace goes. But I'm just, I guess, trying to mimic a situation where you're reverse engineering something and you only have a picture. Okay, so the next thing that you'll notice is that these images don't line up precisely. And so what we're going to need to do is use the cage transform to try and get these to match up. Now, this is a little bit imprecise, and so I'm just going to give it a shot and see what happens. So the first step, if I was doing this right, the first step here, actually, before I do that, I'm going to change the opacity in my pasted layer. Okay, so here we go. Cage transform. I'm going to click in the corner of the bottom layer image. So I'm going to grab each corner with the cage transform. This one has a little bit of an overhang, so I'm going to try and grab that. Okay, so now I've got a cage. It's computing cage coefficients. This takes a while because it's a pretty high resolution screen here. Okay, now we're going to go ahead and adjust these. You know what I need to do? I need to set the layer constraints to match the drawing. There we go. All right, now let's do the cage transformer again. So I'm going to grab here. That looks about right. It doesn't have to be exact. We'll let it compute its cage coefficients again. Done. All right. And we're going to drag those to the corners of the board on the other layer. Yeah, those are RCA plugs, for example. I have not heard tulip. That might be a European designation. Okay, so I'm just grabbing these little handles that I put in the cage transform, and I'm just lining them up. That might have been wrong. Let's see. Okay, now what I can also do is flip this other layer on and off and see those vias. See these little shiny vias here? Let's see how well they line up across the board. That's actually pretty good. That might be close enough. All right, fine, we'll call that good. And so we're done here. Let me complete the transform. So I'll hit enter. Yeah, these I think are not meant to be mounted through the board. These RCA connectors, I think they're actually cable mount RCA plugs, but some very clever designer bought these as a separate part and made a footprint for them on the board. So it's actually a little odd. If you see on the camera, it's got these little wire loops that come out that are basically soldered into the tips of the connector, just like you would a cable, and then they kind of branch down over and solder onto the circuit board here. Very strange. Okay, so here's my circuit. Let's go ahead and close this. Let's go and save this. I'm going to go ahead and stash this somewhere. Sure, we'll call it that. What's the nice number, like 2020-1107, and I guess it's the date. And let's fire up KiCad. Okay, let's create a new project. I'm going to put it in the same folder. Sorry, you won't be able to see this. This is off screen. This is on my other monitor. I'm just creating project. Okay, so here is KiCad. And here's the video schematic. There is nothing quite like a blank KiCad schematic. So many possibilities. And now let's go back to this bill of materials. Let me just sort of squish this down here so I can see both at the same time. And the next step of the process is a little tedious, but many tasks in reverse engineering are. I'm just going to go through and start adding components one at a time. If you've got a 4-layer board and you're lucky, the 2 inner layers are just power and ground, and you may be able to ignore them. I've seen boards where they use some of those power and ground plane inner layers as a cheating way to route a trace or two. And even if they do that, you're probably still okay. You could get pretty darn far with just the outer layers. If you've got any more layers than that, the reverse engineering becomes significantly more challenging without extra equipment, like an X-ray, or you could do a destructive reverse engineering using sandpaper. But that also generates some pretty toxic dust, and it takes a lot longer, and it's pretty hard to get it right. Okay, so the first part I want to put down, I doubt there's a symbol for it. There's an MC1372, but there is not an MC1374. And so what I'm going to do instead is just put down a 14-pin connector, I think on O2X14, and we're going to want to do counterclockwise so that it lines up with a typical IC. Oh, I'm sorry, 07. Okay, that had too many pins. Okay, and so we're going to use this as a stand-in for that first part. And I'm even going to rename it U1. Okay, save. 2x07, thank you, I noticed. Okay, let's get some more parts in here. U2 is a 7808. Let's see if that's in there. Look at that, LM7808. And call that U2. Next one is C1. I like the small ones. I don't know why. I think it's called C_small. Yeah, that's what I want. And again, I also tend to cram a lot of parts onto my schematic sheets. And I don't know what that is, so I'll just leave that for now. Let's do R1. Technically, I should be marking these as I complete them, so I'm just going to go mark them with bold. So R1 is 27K. Should I use the US symbol or the European symbol? I'm going to use the US symbol because it's our day today. I'm sure most of you agree. And I need to put in a value, 27K. And I'm lazy, so I'm just going to make a copy. This one's R9, and that's going to be 39K. Okay, I'll just go through one at a time. Let's keep going. R5. If you have any questions, as always, please don't hesitate to let me know, either by voice or by chat. Got that. Got that. Time for an inductor. That's not the inductor I want. Let's try L. Even better if there's an L_small. L3. Aren't you glad you chose a small board? Okay, so C3 is actually polarized. So I'm going to need a polarized capacitor. Okay, that one is C16. $47.16. It's more fun to do this to music, but I want to avoid triggering the copyright bots. C14. Again, I don't know the value of these surface mount ceramic capacitors, but that's okay. We'll figure it out later. Could have disabled a video from your side all this time. Ah, that was the problem. Yeah, I still don't know all the ins and outs of Zoom. Kind of surprising. All right, so we need R1AN. Didn't we already figure out what that was? Could have sworn we already figured out what that was. No, we figured out the 2A. Okay, so I'm going to have to go and Google this. Let's do AN SOT23 transistor. Let's see what that is. GIMP is available for Windows. Yes, it is. There's even pre-compiled ones. Must include R1AN. It says it looks like there aren't any great matches, and then it has a fine chips result that talks about a surface mount PNP transistor. AN. That was a false result. Thank you, Fine Chips. Just trying to figure out a way to get some smack talking in about Fine Chips because they're, after all, they own Hackaday. So RIAN maybe. Ah, here we go. That looks more promising. Oh wait, no, I picked up on a word here. Variance. Great. Is that N smaller than the R1A by any chance? Well, I don't remember. Let's take a look. Why, yes, it is. That N is smaller. So maybe I just want R1A and leave off the N. Ah, that's bringing up some results of inductors. Let's try R1A. Oh, here we go. MMBT 3904. 3904, mystery solved. All right, so the lesson there was that little tiny letter N was some kind of a package code or lot code or something like that, and not technically part of the top mark. That was good call. Okay, so let's do a MMBT 3904. Look at that, it's already in here. And this is Q3. And next up is C13, which is a trimmer cap. Let's see if I can find, there's a C trim, that'll work. Symbol's a little weird, but that's okay. And I should start bolding ones that I've done already. Our 17 is 100 ohms. Or use a Sharpie to mark all the traces by hand and remove it with IPA afterwards. Yeah, you can do that. I'm just following up with a chat. Most of the functionality may still be hidden within the firmware on the MCU. I do have experience going into the firmware, but I see that there is also a session at Remoticon on firmware reverse engineering. So that would be a good session to attend. Okay, I did C13. Let's do R17. Oh, I already did that one. C question mark. Let's do C question mark. Done. I'll have to come back to that one later. Okay, this one is a 3906. This is Q5. Tomorrow is hardware debugging. No, there is one tomorrow for extracting firmware. Oh, okay. Bare metal firmware wasn't really covered. Unnamed RE podcast is playing. Okay, good. All right. All right. So it's a very complex topic that deserves its own workshop. So maybe someday. But I have used some fairly advanced techniques for doing reverse engineering of firmware. But the typical approach is that you want to extract the firmware from a microcontroller somehow. And there are a bunch of different ways of doing it. Not all of them are practical. Some of them require things like probe stations and fuming nitric acid. And I have done a little bit of that. Oops. Man, I am really having trouble. Okay, so it's R19 I want. Ay, ay, ay. I am Butterfingers today. Okay, so that's R19, and R19 is 680. And copy that again. And this is, I want a capacitor. That is going to be C15. R18 is 390. All right. I'm trying to follow up with the chat here occasionally. Somebody wants to do glitching. Yeah, you can do glitching. It can get really complicated. You have a NOR flash, lucky you, you can just pull off the NOR flash and read that back, but it doesn't always hold all the firmware. It might store configuration information. Yeah, that is worthy of a day-long session for sure. It's just a endlessly complicated topic. Lots of rabbit holes to go into. L1 and L2. Let's do L1 and L2. L1 and L2. L1 is 270 and L2 is 220. I'm actually really excited about this board because I didn't think I would ever be able to use it for anything. It was literally sitting in my junk pile. Okay, CR1. I believe that's just a regular diode. CR1. Bonus points to anyone who knows what CR stands for. Well, CR is a rectifier, yes. But I don't know what the C stands for. Maybe somebody knows. Correctifier, correctifier. And I believe this one is a 1N4001. So I couldn't see the last two digits, and I'm assuming it's an 01 just because this board has not got anything over 50 volts on it. Common, coil relay, crystal rectifier. Ooh, so plausible. I don't think that's it though. That is a tricky one, all right. I got to think about it. Prefixes are fun. R15 is a trimmer pot. Okay, so we're going to need to find a trimmer. R-trim. I don't like that symbol. Let's just use a regular potentiometer. The pinout, of course, on this is not going to match what we have, but that's okay. We'll try and wire it up correctly anyway. And I believe that was a 1K. C11, another one of these little guys. And that is our official half-hour warning going off. I'm definitely not going to be able to finish this board tonight, but I want to at least show you the process of tracing it out. R16, that's a 1K. Oh, so many parts. All right, I'm going to speed this up by moving this over to my other monitor, and I'm just going to focus on getting this done because I want to be able to demonstrate more techniques. So I'm going to go a little quiet while I just sort of hammer this out.
While you're doing that, Eric, can I show a board that I've got and just get some audience feedback?
Sure, let's go and put that up. Where are you?
Okay, this is Andy Gephardt.
Hang on, let me try and find you.
And,
if you turn on your video, it might pop you up to the top of the list.
oh, I'm sorry. Yeah, I know that. Oh wait, no, I got. Yeah.
Oh, there you are.
Okay.
Great. Here's your spotlight.
Sorry for the distraction. Any of you guys know? I didn't have a good board to follow along. This is a prototype somebody made at some point. Do any of these labels mean anything to you guys? Like UCL, DCL? It did have this.
Is there any way we can bring it up like full screen? I have a very small view of your camera.
I don't know. I don't want to distract Eric. He's trying to.
It's already shared as best as I can over here.
Okay.
So there may be a Zoom setting on your side. I'm not familiar enough with Zoom to be able to tell you exactly what.
There's a view options thing at the top, and you can change it to side-by-side mode, and then you can change the ratio of sizes between the presenter and the person talking. You can get it a little bit bigger that way.
Nice.
Thank you. And got it figured.
Yeah. I don't know. It's just kind of a random question. There's a bunch of buttons. There's a red LED. It's a momentary button. And
Oh, those are cool.
Yeah, they are funky. And then there's safe, INS, and IDS. It seems like it was a test board for something. There's also a pass. It says pass up here. Just thought you guys might go, oh, I know what that is. To relay a bunch of lights and buttons. It's about it. Oh, and then this is, the routing is interesting.
Literally hairy.
Yeah. I've been picking up a lot in this. One of the things that I was listening to earlier was the, like, how do you figure out what a component is when it's not labeled? The resistor capacitor. Oh man, there's no secret way to do it other than pull it off and check it. Oh wow. Anyway.
Yeah, in-circuit measurements aren't always possible, depending on what the schematic looks like. So if there's nothing connected to the other end, like if it goes out to a connector or something, then you can measure it in circuit. Otherwise, it's not really going to work.
All right, I'll go back to quiet mode here.
Thanks for sharing.
Yeah.
And I'm back again. I'm almost done. I got a couple more parts, and then we'll be able to move on to the next part. Okay, R2. I have 60. See, if I had planned better, I would have done this in advance, but where would be the fun in that? And R7, I think, was 50. Is that right? That sounds like a mark. R7. That's the mark. This is actually 75 ohms. I made a mistake there. R2 is 560. The reason I did that correction is because I was expecting to see a 75 ohm series termination resistor in there somewhere. And so that was my experience saving my butt. Sometimes it does that. Okay, here's another electrolytic. That one is C4. All right, now we're off to the connectors. Let's do a coaxial connector for J2 and J3. J2 is audio. I can spell sometimes. J3 is video. Okay. Those two connect. Oh, there's still more parts. There's a C. See, I'm just putting them wherever. C2. Okay, now we have DC in, and that's a 2-pin header. So let's do a con O2X01. Which one looks nicer? Who cares? I'll use this one for now. We'll call that one DC in. That one's done. And then there's IR and switch. IR is 2 pins, and switch is 4 pins. Okay. Now let's place the 4-pin connector. You know what? I should have used the other con 01 X04. See, now I'm regretting the connector choice already. That's okay. Switch. Okay. So that is basically it. All right, let's save that, save this. Now we're ready to get into the tracing. So my bill of materials is basically done for now. So let's go ahead and set that aside. Let's see. Okay, people are sharing links for LRC meters. That's great. Awesome. Oh, that's not too bad. That's not that many parts. So here's what I'm going to do first is I'm going to rearrange things just a little bit. This chip is clearly important, so that will go in the middle. And then I'm going to move those other parts off to the side. So let's go ahead and start. So let's go back to the GIMP image here. I'll create a new layer. And let's call this a trace layer. Make sure it is transparent. So it's filled with transparency. You all can see my screen, hopefully. Yeah, I'm sharing. Good. OK. And I'll just grab a pen and start tracing. Sure, why not? Size 1. Let's make it. Let's try 10. Let's get a nicer color. OK. Should I start with a 7805? Maybe I should. Actually, let's start with +12. That's always a good place to start. So make sure I'm on the trace layer here and draw a nice little line here because this net will be done soon. So let me grab the connector. Here's DC in. And there's a nice keyboard shortcut, which I'm forgetting, that will jump you directly to that part. Maybe it's Control F. CR1, there we go. Look at that. Is that CR1? I need to look at the board. No, it's CR2. CR2. So move CR2 over here. And let's actually flip this because pin 1 is probably, sure, I'll call that pin 1, whatever. Not too important. So that comes in through diode. This is ground, so I'm just going to use a ground symbol here and assume that that's what it is. Boom. So that's done. So we're here, and now we're onto this plane. So this plane area here is 12 volts through a diode, and that goes to C2. So let's go and grab C2. Where was C2? C2 is here. So I still don't know the value of it, but again, that's okay. So we'll go ahead and put that in. We don't know where the other end goes, but that's okay. We'll get to that. Okay. And so continuing on. Oh. So I did a bunch of things wrong here. And what clued me in was the fact that this is running to pin 2 of the 7808. I have the polarity of the diode backwards. And it looks like the silkscreen marking is wrong. No, the silkscreen is correct. This is a reverse polarity protection diode. So it's not a series diode. So let me go ahead and fix that. So that should be pointing up into it. And what I've found is actually the 12-volt rail. And so this is ground. That was a good catch. Okay, so that is indeed ground. And pin 1, it looks like it goes to a bunch of circuitry, which I will have to figure out at some point. So that comes in off of switch. Yeah, really what I want to be doing is tracing this 12-volt connection, because this pour right here is just ground. So in fact, I'll just make a copy of this and we'll ground that. Yeah, pin 1 is often square, but not always. And diode polarity, I'm using the mark here on the end. So that stripe there corresponds with the cathode of the diode, which is that line on the symbol. Okay, so let's look ahead at the bottom layer. So I'm going to change the transparency. I don't see this going anywhere. Huh, that's really odd. That is not what I expected to see. Yeah, this trace doesn't seem to go anywhere. I must be missing something. Well, I have the board here physically, and maybe there's a trace and I just can't see where it's going. And so I'm going to go, oh, there is a trace. Okay. So here's what's going on. There's a trace that goes up to this DCN connector here, and it hooks around and goes to this diode, which is CR1. Yeah. Okay, that makes sense. So this capacitor is not supposed to be there. And instead, we have CR1. And CR1 goes here. So let me go ahead and rotate that. I'm hitting G to drag it, so it drags the trace. All right, so that's a series diode. And that winds up here where this dot is. Now we're back into things. Okay, all right. This makes sense. So this is all plus 12 volts. And that goes to the input of the voltage regulator. You know what I'm going to do? I'm going to use a plus 12 volt net symbol. Plus 12 volts. We'll use this little flag. Great, and I'll make a copy of that. Okay, now let's see what other components are here. So there's this other part here. Looks like there's a resistor. And which resistor was that? That was R19 or R18, one of those two. That's R18. So one end of R18 is plus 12 volts. There's R18. CR crystal rectifier differentiates from a tube rectifier or a selenium rectifier. Vintage electronics holdover. All right, so that other person was correct. It is crystal rectifier. Wow, that's a good one. Today I learned. Yeah, back in the day, it would have been a vacuum rectifier, right? Vacuum tube. I guess I probably should have known that. Okay, let's make a copy of that. And that goes to 12 volts. I don't know where the other end goes yet. So it's probably some bias circuit. And then there's C15. There's a bunch of other parts on 12 volts. And now that I think about it, I think this Motorola part runs off of 12 volts. So that's probably all going over there. I don't know what they use that 5 volt regulator. Oh, I guess they use 5 volts as well. All right. All right, so let's go ahead and trace things out some more. So C15 also goes there. C15. Probably would have been more interesting to start from the chip, so I might just do that. So after I copy this over, oh, it goes into a transistor. Q5 pin 2. That can't be right. Is that really the emitter? Let me think about that. Base, collector, emitter. I'm suspicious. This is probably the collector. So I'm not sure what that transistor does, but I'm sure it's something interesting. The pin numbering I'm not expecting to match up. Oh, actually, you know what? This is a PNP, so I might have gotten it wrong. All right, well, you know what? Here's what I'm going to do. Since I'm an impatient guy, I'm going to go back to this chip, and we'll figure out some interesting connections there. So let's go ahead and look. Is that pin 1? Yes, it is pin 1. So pin 4 goes up here to the output of the 5 volt regulator. So now we need a 5 volt flag. And let's wire that up. I hope you all are doing this on your board too, getting a head start on it, because now is the time to ask me questions while you have me available. So you don't want to run into a situation where tomorrow you wake up and need to reverse engineer the board the rest of the way and then get stuck on something, except Eric's not here for questions, which means you'll have to find me on Twitter or something. I don't know. Looks like it goes to a bunch of other parts, but we've got that trace in, so that's good. This plane is ground, and that is pin 5. So pin 5 is ground. Let's see if there's a ground symbol I can steal. Great. So that takes care of that. Now, there might also be ground connections on the top layer of the board. So that's something we have to watch out for. In fact, I may actually have to go in with a multimeter and buzz out those connections. What was that? Dropping off Twitter? No, I'm staying on Twitter. It's awesome to see the process in action, especially when Eric is dealing with the unexpected in real time. That's what I'm trying to do. I'm trying to talk about what I'm working on as I'm working on it.
Eric.
Yes.
Hi, this is Sophie. I'm just popping in because we are. Hi. It looks like this is going great. I'm seeing stuff fly by on Twitter. I wish I could be here. This looks like very informative. How late is this going?
We're going to get as far as we can on this particular circuit board, and then we're going to wrap things up on time. So I'll probably do this a couple of more minutes, and then we'll maybe conclude, have a little discussion or something, and it should all be done at 6:30.
Okay, that sounds good. Just checking.
Thanks for checking in.
All right. See ya.
Bye. Is she gone now? Okay, great. We can get back to it. I'm just teasing. Okay, so we need L3. See, I'm getting in trouble because I'm taking too long. But now you're getting the idea of how long this sort of thing takes in real time. There's a couple of things that I did want to do. So when we hit the 620 mark, I wanted to discuss this circuit from kind of a top level perspective. That goes to pin 3. And the reason is that there's some really interesting pieces of the circuit that, based on experience, I kind of have an inkling of what they might do already. And that goes out to R12. Was that the other end of it? No, that's the same end. Yeah, some couple of interesting observations that I wanted to share with you. So Control F, R12, since I already placed it. I can do this for hours, and I have done this for hours. You know, I get music going, or I put a Netflix on in the background, and I just churn through it. I need to put a gap in there. Those are not the same trace. But again, I'm just using this to mark what I've done so far. This isn't really the source of truth for the netlist. Okay, so that also goes down to the trimmer capacitor, it looks like. But I have to look at the physical board now because otherwise I can't tell. Yes, so it goes to one leg of the trim cap.
Hi, Eric.
And the schematic is going to look super messy, but it will tidy up soon. Yes.
So I have a mostly SMD focused, entirely SMD based board.
Okay.
I suspect a lot of the traces are going underneath the ICs.
Yes.
They're like SOPP like 20s and stuff like that.
Sure.
So and because it's got a plane of like ground plane on the other side, it's hard to shine a light through to see.
Yes.
Any recommendation on which ones to take out first? Like what would be the best order of operation?
So if it's thoroughly documented and you've got pictures of it, then it's okay to start removing components because you know where they go when you want to put it back together again, if that's what you want to do. If you don't care about it functioning when you're done, then just go ahead and tear into it. But just make sure you take lots of pictures before so you know where everything goes. I'll give it a couple more minutes and then I'll tell you what my overall impressions are of the board. You know what? I'm going to do that right now. And then I'm going to open up the floor for questions that people might be saving up. So I did have a couple of observations about this. The circuit so far looks really similar to the data sheet. This is the wrong window. I wanted to pull up the data sheet. Here we go. And so this schematic right here, yeah, so you can start to see, like, here's a coil, there's a trimmer cap. It's starting to look very, very similar to the simplified application circuit. And if I scroll through the data sheet, I'll probably see a couple of pre-cooked examples Well, this one doesn't seem to have any, but there may be an application note that goes into more detail. But already some of the connections are starting to look familiar. Yeah, so this has something to do with sound. And so what I'm putting together here is actually the sound circuit. So one observation is that if you've got a good data sheet for one of the parts on your board, and that's like the sort of focus of the board, the main chip, if you will, often you can learn lots of interesting things just by reading that data sheet and familiarizing yourself with it. Another interesting thing to look at on the circuit board is that they've got some kind of a power switching circuit. I think it's power switching. It might not be. Yeah, there's a transistor in here, and probably some sort of a series transistor to limit the current, or sorry, a series resistor to limit the current, and it goes into what looks like some kind of a filter. Yeah, so that looks almost like a pi filter. So you've got two inductors with capacitors going to ground. That might actually be shutting off some video signal coming out from this chip just by clamping it to ground. And then R15 may be some sort of a bias adjustment. And then if we go over here, okay, this is what I wanted to look at. This looks a lot like a differential amplifier. Let me toggle between these two views so I can see. Yeah, it kind of does. So there's a voltage divider up here made by R4 and R8 that goes from this connection here to ground. And then that goes into probably the base of this transistor here. And then you've got an emitter transistor here. The collectors are tied together. And so that's kind of the classic long-tailed pair that you see in a differential amplifier. In fact, if we go back to the data sheet of this part, here's a couple examples of some differential pairs. So let me zoom in so you can see that. So there's two transistors. In this case, they're sharing an emitter connection. Here it might be the same. It might be a shared emitter, although I'm not sure this is quite right based on the pinout. Yeah, these might actually be two different amplifiers. Let's see. Yeah, so they're sharing the same pin on the collector. That's what's messing me up. And then that goes into the base, and this base goes into here, and that might be some sort of a follower circuit. So I'd have to trace it out further to understand what's going on. It probably is an amplifier for the video. So we could start from video and then kind of go backwards. So there's a resistor to ground. That's our termination resistor. Looks like there's a capacitor here. Okay, so there's a series coupling cap, and then that goes in here to this voltage divider, and so that's our bias network. And then it goes here to this transistor. All right, so I'm gonna have to check the pinout for those transistors. Oh, I know what's going on. I got this backwards. I was assuming that this is a video output. This is actually a video input. So video from the VCR comes in, goes into the 75 termination resistor, 75 ohm termination, goes through the series cap, then it goes into this amplifier. So there's your bias network there, and that sets up the Q point of the transistor. That goes into the base of Q1, and Q1 is a common emitter amplifier with some emitter degeneration, and so that linearizes it and basically controls the gain. And then that goes over through here to this circuit. I'm not sure what this transistor is doing. It might have something to do with that little video enable circuit that we were looking at earlier. I'd have to trace out the schematic all the way to figure that out. And then trying to follow the signal chain, it goes in here, and that looks like it might be some kind of a follower circuit, like an emitter follower buffer or something. So there's a resistor here that goes to some kind of a power rail probably. Yeah, that's probably a power rail. And then that goes through this LC filter, and then that probably goes into the modulation circuit. Yeah, so I think that's what we're looking at here. So we've got about 5 minutes left, and I want to use this time to answer anyone's questions that they might have about any of the reverse engineering that they've gone through so far in this session. I'm going to scroll back too if nobody speaks up.
So I was wondering, you mentioned desoldering parts.
Okay.
What would you be doing? Like if I want to desolder my IC, is it to look underneath where the traces start, or is it to...
Yes. So you're desoldering the part because you want to see where the traces and vias are underneath. So if you've taken a picture of the back of the board and you see that there's a via there and you want to know where it goes, then you'll have to remove the chip that's on the opposite side in order to figure that out. Another way to do it is, if you suspect it connects to the chip, is you could put the multimeter on the via and then put the other terminal of the multimeter on each of the pins of the chip in turn. And so then when it beeps, when you see 0 ohms, then you know that the trace is connected to that pin. So in this example here, there's a trace that comes in from the top and it disappears underneath the chip. I can't tell where it goes. So it could go to any one of these pins here. And so one of the things I could do is shine a flashlight at an angle underneath and try to get a glimpse of where it goes underneath. I could also go in with the multimeter and use the technique I described. And so what I would do is put one multimeter probe on this lead, and then the other, I would sort of brush it across all the other pins to see where it triggers. Hopefully that answers your question. I routinely look at iFixit.com teardowns and repair videos for mobile phone designs. Sometimes I see a dark film. Yeah, so sometimes they use that for EMI suppression. And so they use that to absorb radiation. Okay, we've got 3 minutes left, and then we have the keynote. So one last question. Q2 is probably a switch that cuts off the video, yes. I'm going to scroll back and find questions unless someone speaks up.
Hey, Eric.
Yes.
It's Jen. I asked this question a couple times, but I wanted to hear specifically your opinion. Are there particular vintages or industries that this technique just isn't going to work very well?
Probably. So if you're dealing with vacuum tube equipment that's got all sorts of point-to-point wiring, then this is not really the best technique. You could do the bill of materials the same way, but you're just going to have to trace wires or spend time with a multimeter buzzing out all the connections. And then I would just draw it up on paper. You could do a schematic in KiCad, but that would be pretty challenging. I really appreciate all of you coming. This was a really fun time for me. It reminds me a lot of the Twitch streams that I've been doing recently. So typically on typically Friday afternoons, like 4 p.m. Pacific time, I'll set up a Twitch stream on whatever project I'm working on. Also be sure to follow me on Twitter, because that's where I announce those Twitch streams. And I really appreciate all you coming and asking such great questions. And I'm going to go and hang out in the Hackaday chat room so you can ask me more questions afterwards. And my Twitter handle is @TubeTimeUS. I just pasted that into the chat room. So thank you all so much for coming. I really appreciate it.
Eric, thank you for hosting this walkthrough for reverse engineering a PCB. I got a lot out of your tips and tricks, and thank you for sharing your recommendations and your process. It was very informative. So I think a lot of people can say that in the chat room as well. And again, I'd like to invite everyone to go to the hackaday.io page and continue the conversation there with more questions and comments.